Hello, Algebra 1 students, and welcome to your last lesson for your first topic of Algebra 1. As a reminder, your first topic was solving equations and inequalities, and we spent about 4 or 5 days working through equations. And then the last 2 days, you've learned about inequalities. And first, 2 classes ago, you solved inequalities that look something like, we'll do like 2x plus 3 is greater than 10. And you worked on solving and graphing those. And then last class, you got a nice introduction to compound inequalities, where you practiced writing compound inequalities with or and you said something like x is less than 3, or x is greater than or equal to 5. And you talked about what those solutions meant and how you can graph them. Well, today we're going to try to put our last 2 lessons together. And this lesson is going to be solving compound inequality. So it's going to work with this compound inequality we learned about last class, and you're going to actually have equations to solve that have more than one inequality sign. Now, you should have a copy of the notes for today. There are 3 pages to the notes. Because this is not done on Edgenuity, you don't have multiple slides. This is all one video. What's going to happen, though, is on various parts, I'm going to ask you to pause the video, work through a couple problems, and then unpause the video. When you unpause, I'm going to go through the problems that I just asked you to work through. And at that point, it's your choice. You can watch the video on a faster speed and just make sure you got the questions right. Maybe skim through and get to the next section. Or you can listen to me re-explain the problems. Or maybe you didn't know how to do the problem and you need to listen to my explanation and you can follow along from there. You will need to turn in these 3 pages to get credit for your physical day and your digital day, and your teacher can fill you in how to do that. So let's get started. Your opener has 4 questions here. You can see question 1, 2, 3, and 4, really A, B, C, and D if you want. For A and B, your goal is to do 2 things. First, you'll need to list 3 possible solutions that fit the compound inequality. So for example, this tells you that x is allowed to be less than -8, or x can be a value greater than -8. And your goal is to figure out what are some values that work with that statement. Then the second part is you need to go through and actually graph the full solution. So you need to use the number line that's there, number it, and get those graphed. So go ahead, take a minute or 2, work through those, pause the video, and then once you're done with those 2, unpause the video, and we'll see how you did. Okay, you should have worked through these. Let's make sure we're comfortable with what each of them are saying. Our first one says x is allowed to be any number that's less than -8. And maybe I'll just try listing some numbers that are smaller, that are more negative than -8. And that would be numbers like -9, -10, -11, and so on and so forth. But then it says, or x can be a number greater than -8. What are numbers bigger than -8? Well, those are more positive numbers like -7, -1, 1,000. Those are all numbers that work for the other side. But the problem here is it possible to get a number that's smaller than -8, but that's also bigger than -8? Well, I don't think so. However, that's why we have the or here. Or means we only need an x value that works with one of these or the other. It doesn't have to work for both of them at the same time. So let's take a peek at this. If we look at this first one, x is less than -8 or x is greater than -8, I think actually any of the numbers I listed here would work, right? Any of these 3 are good solutions. Any of the other 3 that I listed, -9, -10, and -11, are other solutions. I've actually listed 6 solutions here because they satisfy or work in one of those 2 inequalities up above. And sometimes you'll see solutions listed in these cool little curly braces, these sideways seagulls, and that's just to show we're listing a whole bunch of numbers. All right, well, how do we graph that? Well, when we go through and graph something like this, I always like to take the number or numbers that are given to us in the problem and use that as really the center of my number line. So I think -8 is going to be right about here. I always put the positive so we know we move right to get more positive, negative to move more left, and then we can fill in a few, right? Something like this. Very nice. You could go by 2s or 3s or whatever sounds good, and if you don't want to fill in the number line, that's not that big of a deal, but you definitely need a couple numbers so we can check to make sure you know which way the negatives and which way the positives go. Once you've labeled your number line, the next step is to take a circle and place it around the number or numbers that you're interested in. In this case, we're only interested in -8. Then, to graph a compound inequality, we just take each piece separately. And we say, okay, well, what are x's that are less than -8? Well, less than, that's more negative. Less than -8 are like -9, 10, 11, 12. I think all the numbers to the left of this are less than -8. And so we get to shade all of this in. However, there's a second part to this, the or part, which says x's can also be greater or larger or more positive than -8. And I think those are all the numbers to the right. So we would shade in this number line everywhere except for -8. Notice that we didn't fill in -8. There's not a closed or a solid circle there. And there's no closed or solid circle there because neither of these say that you're allowed to be equal to -8. So we just use that open circle to really represent like a force field around -8. Say we can be one side of it, we can be the other, but we cannot be equal. Let's go ahead and see how the other one looked. Our other one said, oh, this one's a little bit weird. Notice that our first one told us an or in the middle. Now, what you learned last class, and I'll zoom in on this, is that this is a shorthand way to write an and statement. So we could read this forwards, and if you read it forwards, it says 9 is less than x, and x is in turn less than or equal to 10. But you can also read it backwards. We could say that 10 is greater than or equal to x, and x in turn is greater than 9. And so depending on if you read it forwards or backwards, you're either reading less than signs or greater than signs. And I think that might help for when I rewrite this right now into an and statement. An and statement is telling us that not only does, and I'm going to read backwards here, not only does x have to be greater than 9, and now I'm going to read the other way, and x has to be less than or equal to 10. And so when you have those two combined like that, it's always an and statement. An and means both of these statements have to be true, or meant only one of them. This one means both. So both statements have to be true. Well, let's just try to write out a few numbers for each statement first. Let's start with x being greater than 9. What are numbers greater than 9? Well, 10, 11, 12, and so on and so forth, right? What are x's that can be less than or equal to 10? Well, we can be equal to 10, so that would work, but then less than means smaller. And so we'd go this way. All right, well, we need to list 3 solutions that work in this, numbers that are greater than 9 and smaller than or equal to 10. Well, let's look at the numbers that are greater than 9. 10, well, 10 is greater than 9, and is 10 less than or equal to 10? Yeah, 10 is also equal to 10. So I think one of my x solutions here could certainly be 10. Let's try the next one. What about 11? Well, 11 is greater than 9. Is 11 less than 10, though? And I don't think it is. So I think 11 actually doesn't work as a solution, and neither does 12 or 13. So let's maybe look on this red side over here. What if we thought about 9? Well, 9 is certainly less than 10, so that's good for the first part. And is 9 greater than 9? Well, no, it's not. 9's equal to 9, but it's not greater, so 9 doesn't work. What about 8? 8 is less than 10. Good so far. Is 8 greater than 9? No, 8 is less than 9, so that one's out. In fact, all of these are out too. Does that mean there's only one answer to this? Well, actually there's not. There are an infinite number of answers here, and it may help you to look just at the original problem again. It says x has to be between 9 and 10. Well, we already got 10, but aren't there other numbers between 9 and 10? Aren't there like 9.1, 9.5, right? 9.99 repeating. And so I think you might start to see some more values, some more numbers that will satisfy the original inequality. There are many, there are in fact an infinite number of numbers between 9 and 10. You just need to make sure you carefully read that inequality to understand what it's asking. Now, how do we actually graph this inequality? Well, you could take the two numbers on this graph. You could take 9, and then you could put 10 right here. And you could just have those two numbers if you wanted. I'm going to do a little bit more space, just try to use the space a little bit more nicely. Maybe I'll go by 0.2s, why not? And so we'll maybe start here and we'll say, okay, that this is 9, and here's 9.2, 9.4, 9.6, 9.8, here's 10, and then we'll continue, right? 10.2, 10.4, 10.6. Those are the positives, and then if we wanted to go more negative, we have 8.8 and 8.6. I'm just using this so that I can efficiently use the space on the number line. It just looks weird if you have two numbers right next to each other and then you're done. So I just spaced out the 9 and the 10. How do we start? Well, we put open circles around each of these values, and then we look at those open circles and say, okay, is x allowed to be equal to 9? Well, no. X has to be greater than 9, strictly greater than. There's no equal to, so we keep it open. Does x have to be equal to 10? Well, it can be equal to 10. It says x is less than or equal to 10, and because there's that equal piece, we fill this circle in. From here, we need to go through and actually shade. But where do we shade? Do we do like what we did before and shade on either outside? Well, the values we're looking at are between 9 and 10. Between 9 and 10 is, as you'd probably guess, shaded between 9 and 10. And there we go. Now we have our compound inequality. Now these two should have been reviewed from last class, and if they don't seem familiar, you might want to go back and redo that edgenuity lesson, your intro to compound inequalities. I think it might make this make a little more sense. But now we get to parts C and D. So first, you're going to have to list 3 possible solutions, and then you have to write a compound inequality that represents what's being graphed. Go ahead and pause me, try that on your own, and then once you have your solutions, unpause. Hopefully this wasn't too terribly difficult now that you've unpaused. Let's list a couple answers here. We have to go between -3 and +4. -3 could be a solution, right? We have a closed circle here. That's good news. +4 could be a solution too. We'll maybe list that over here. That's a closed circle. Then anything in between. So I'll pick, I don't know what's in between that. I think pi is in between, isn't it? 3.1415, that's in there too, just so that I can be unique, right? You shouldn't just copy my answers down, right? Pick some others. You could have picked 0 or 1 or 2, so be creative. Now a compound inequality that's going to represent this. Well, let's take both pieces. We can see that the x has to be greater than or equal to -3, because we shaded to the right, and at the same time, the x's had to be less than or equal to 4. And although this is an acceptable way to write your answer, you're almost never going to see it written like that because we have a more efficient way to write it, and mathematicians are lazy. We like the most efficient way possible. So the way we'd write it is we'd say -3 is the smallest, 4 is the largest, x is in between, and then, well, which way did the inequality symbols go? Well, this first one is easy. It's that x has to be less than or equal to 4. Right? Notice that the greater than sign is trying to eat the 4, right? Teeth, if I zoom in and you had some cute little teeth in here, right, is trying to eat the 4. So they need to be doing the same thing over here. We're going to use that same strategy to understand the other inequality sign. It says x is greater than or equal to 3, and again, the teeth are trying to eat the x. So when I draw this greater than or equal to, the teeth better still be facing that x. And it looks kind of weird because you're like, wait, it's a less than sign. But remember, if you read it starting with x first this way, it's x is greater than or equal. And if you do it this way, it is x is greater than or equal. Because depending on which way you read your answer, you have to read the inequality sign differently. Last but not least, we have this cool guy over here. Notice that there are 2 open circles. So I think maybe I'll do this first one right here. It looks to me like the x's. Oh, no, wait, we should do some solutions first, huh? Well, it looks like anything that's shaded is a valid solution. I can't use -4 or 0. Those are open circles. But I could use -5. That's on the shaded part. And then I could use 1, and that one's okay. And then there's an arrow. It goes forever, so why don't I use something a little more creative like, I don't know, 75. I think all of those will work. As long as you don't pick a value between -4 and 0, I think you should be good to go. How do we write this? Well, our x's, and we'll do this one over here on the left first, our x's had to be less than -4, right? That's where -5 worked. Also, our x's could have been values that were greater than 0. But you'll notice that the values we picked, like 1, which is over here, that's not both smaller than -4 and greater than 0. No, I think 1 is only greater than 0. And so in order for a solution to work here, it has to work with one of those two. And we don't have a shorthand way to write the or, so this is how we write our final answer. All right, now a little bit of a challenge for you guys, because as we learned with equations, there can kind of be inequalities, well, and there definitely can be inequalities with infinitely many solutions. And when I say kind of, I mean realize that this has infinitely many solutions up here, right? There are an infinite number of numbers between. But what I mean for infinitely many solutions is we wouldn't even have restrictions. It would really just be every single number. Or you could also have inequalities, of course, with no solution. So we should probably look at those two quickly. There are 4 problems down here, very confusingly all labeled A, and A, so I'll hopefully update this before you get your worksheet. Please go ahead and see if you can create an inequality that does each one of these things. For example, the first one says, write and graph, and it might be easier to start with a graph, a compound inequality that uses OR and has no solution, meaning you shade none of the number line. And then B asks you to write one that says or and shades the entire number line. And then C and D both ask you to do the same thing, but with and. So let's see what you guys can come up with. And then once you've tried all 4, you might not be able to figure out one for all 4 of them. We can come back together. All right, so hopefully you've tried all of these at this point. Let's just go in order. Let's start with A, the first A. We want a compound inequality that uses OR and has no solution. Well, I think this one's going to be pretty tough. I think if we said x is greater than, let's say, 5, I mean, you already have an infinite number of solutions here. And then if you said or, I don't know, x is less than 5, less than 7, okay, any of those, I think that those are all going to have solutions. You're going to be shading on your number line, and in fact, I would probably argue that this first one is not possible. So if you see an inequality that has or in between, you are definitely going to be shading somewhere on your number line. Well, what about B? Write or graph a compound inequality that uses or and shades the entire number line. Oh, I bet we could do this one. Check this out. What if I said x is greater than 1, or, and then you could do a pretty easy one. You could say something like x is less than or equal to 1. That'll get all of your numbers. But watch if I do this. Let's say x is greater than 1, or x is less than, let's say, 4. I should do these in 2 different colors. I think we can see it on the number line then. X is less than 4. Well, I'll zoom in here and let's take a peek. So it looks like 1 and 4 are important for my number line. So here's 1, 2, 3, 4, and I'll continue the rest out. I don't think you need to hear me count though. We'll get some negatives in here. Well, how do we start? We of course start by putting our open circles around each of these. And then we'll just do one at a time. X has to be greater than 1. Well, greater than 1 are all the numbers to the right of 1, including 4. So by crossing over 4, what I'm really doing here is, even though I started with an open circle, this greater than 1 part is going to cause this circle to be filled in because I'm including 4. Now, I'll leave that off and I'll go back in and do that later on. It might be a little confusing, but let's take a look at the second part. It says, or your x value has to be less than 4. Well, less than 4 means go to the left. And you're like, well, we already shaded that part. Great, now it's double shaded. Super exciting. And we're going to keep moving left, and we get to this other part. And I think you'll notice that the blue part, less than 4, definitely includes 1. And as we mentioned, greater than 1 definitely includes 4. And look, now we have a number line that's completely filled in. So it is definitely possible to get something with infinitely many solutions. However, I don't really like writing it like this because, again, all of our inequalities have infinitely many solutions. So instead of infinitely many, because up here we might have said there are infinitely many solutions as long as the values are between -3 and 4, we might want to say infinitely many solutions. Instead of that, we might just want to say all real numbers. And as a reminder, real numbers are just all the numbers you know put together. Positives, negatives, decimals, fractions, zero. What all real numbers mean is you can use any number you can think of and it will work in one of these two equations. So sometimes you'll hear all real numbers instead of infinitely many solutions, and although they generally mean the same thing, there is a small difference there. Let's go and look at these last two. Write and graph a compound inequality that uses and has no solution. Well, no solution. Let's do something like this. Let's say that x is, and we'll use some colors again, let's say that x is less than 2, and, well, what's something that would be impossible? Well, for our answer to be less than 2, and let's also make the answer greater than 5. Let's see what happens. So I'll go through and I'll number this again. So we'll just say something like 2, 3, 4, 5. And again, we'll continue out, always putting the positives so we know which way the positives go. Our positives should go to the right, negatives to the left. Open circles on 2 and 5. But then let's think about it. Let's think about the values that work here. Because for an and really should be shaded in between two values like this up here. And so what this is telling us is our x's have to be less than 2. And so think about this section over here. These are the values of numbers that are smaller than 2. And your x's have to be greater than 5. Well, can you think of a number that's smaller than 2 and greater than 5? Hopefully not, otherwise you might have just invented a new field of mathematics for us. You'll notice that none of the numbers in the blue circle overlap with any of the numbers in the red circle. And so this would be a really nice example of an inequality, a compound inequality that has no solution. There's no x value that will work in both of those. Let's get on to our last one. Write and graph a compound inequality that uses and shades the entire number line. Oh. Is this one even possible? I'm not sure it is. I think this is going to be really tough to do. I think, are going to have some trouble because if you say x is greater than 2 and this is 2, that means all of your numbers have to be greater than 2 and something. Well, I think the and something is going to exclude numbers over here, so you won't be able to shade in the whole number line. So I think this is actually going to be something that is also not possible. Now, I don't think any problems here are going to try and trick you. You're probably not going to get any ones like A and D here. However, it's certainly possible that you'll get problems where you either shade the whole number line or none of the number line. So keep that in mind. A and D are really just little bonuses, but B and C definitely happen. Now, when I say happen, you might be asking, what are you talking about? We already know all of this. We've covered it. All we have to do is graph. Well, there's a little bit more to it because not every compound inequality is given to you so nicely where they say it's between 4 and 7. You're like, great, wrote that. I'm a winner. Well, you're still a winner, but sometimes these problems are presented as equations where x isn't isolated. So we're going to do two examples together, these two right here, and then you guys are going to tackle the rest on your own. So let's rock and roll. Our first problem tells us that -2 has to be less than 2 times whatever x is minus 6, which in turn has to be less than or equal to 4. But the problem is that doesn't really tell us what x it has to be between. It tells us what 2x minus 6 is in between, but down here on this number line, we want to graph specifically the x values that x is in between. And you could guess, you could say, well, I think x has to be 10. Well, let's see if that works. -2 is less than 2. We said x is 10, so 2 times 10 minus 6, which is less than or equal to 4. And then help me out with some mental math. 2 times 10, 20. 20 minus 6, 14. And so we see if we're right. Is 14 a number that's in between -2 and 4? Oh, no, I don't think 14 works, which means x equals 10 is not a solution. We're not going to shade 10 on this number line. But it would be really tedious, really obnoxious to have to just guess and check all the x's. So we should be able to use our algebra skills here to isolate x to see exactly what x is in between. Here we go. -2 is less than 2x minus 6, which is less than or equal to 4. Currently, this equation is perfectly balanced. 2x minus 6 is in between -2 and 4, and we need to preserve that balance as we go through to isolate x. Now, traditionally with equations, you've only had one equal sign or one inequality sign, and now we have two. But our rules of algebra still apply. What I'm going to do is I'm going to use a line here so that we can see the number of sides on this equation. Notice there is a left side, a middle side, and a right side. So we have three different sides here. And so when we go to isolate x, we really need to make sure that we do the same operation to all three sides instead of just two. Now that might seem complicated, but I think it's easier than what you're giving it credit to. So let's look at the three sides. -2, there's no distributive property, no like terms. We look at our center part, there's no distributive property, no like terms. We look at the right side, there's no distributive property, no like terms. So we've already skipped through the first two steps of solving any equation. And then our last step when we go through and solve an equation is we just find the side with x and we work backwards through SADMAP. Though this semester we don't do any exponents or parentheses. Okay, so working backwards, which side has x? Well, this middle side has x. There are two numbers attached to x. 2 is multiplying, 6 is subtracting, and following SADMAP, we undo addition and subtraction first, so I think that means we need to add 6. Now, if I want to add 6 here, that will of course just leave me with 2x. I think we need to keep everything balanced, like all things should be. So we need to add 6 here, and of course add 6 over here. And that gives us a 4, and 4 and 6 gives us 10, and then these are still here as well. Okay, well, is x isolated? No, there's still a 2 multiplying by x, so now we've moved down to our second one. We're going to divide everything by 2. You should ask yourself, do you need to flip the inequality sign? But you don't. We didn't multiply or divide by a negative, and so now we have our final answer. We see that x has to be some value between 2 and 5 in order to work in the original relationship. Let's go ahead and graph all those values that x is allowed to be. So we have 2, 3, 4, 5, nothing too crazy here. Here are my positives. There are the negatives. We have 2, which I'll do in blue, and we have 5 that I'll do in red. We have to think if either of those circles are closed or filled in. I think x is not allowed to be equal to 2. There's no equal sign in sight, so that stays open. However, I think x is allowed to be equal to 5 because there is an equal sign there. So it looks like this. X has to be between 2 and 5. You can tell because it's between 2 and 5. X is greater than 2 if you read from x to the left. X is smaller than 5. So greater than 2 goes this way. Right? And you could extend this all the way if you wanted, and smaller than 5 goes this way, but x has to be both at the same time. So where do they overlap? Well, they overlap right in the middle. And this shows us that x can be any number greater than 2 and equal to or smaller than 5. All right, well, what if we got one that had or? Because technically that one had an and in it. If we're looking at or over here, the nice part with or is because each statement is separate, either x can work in this one or x can work in this one. You can just treat them as two completely separate problems. So it's always tough. Sometimes I draw a line down the middle, but then someone's like, oh, we need to divide everything by -1, and they divide all the sides by -1 over here. That's not what we're doing here. So what I'm actually going to do is I'm going to treat these as two completely separate problems. So I'm going to go ahead and just say, you know, we're going to have, I don't know, let's do something like this. We're going to have one problem over here, -x is greater than or equal to 3, and we'll have the other problem, -3 is less than 3 times the quantity x minus 2 over here. Two colors, two completely separate problems. We don't have to do whatever we do to the red equation to the blue one as well. Maybe even on your paper, cover up one problem so it doesn't confuse you. Okay, let's go ahead and isolate x for this red equation. Well, what's attached to x? There's a negative, but it's got to be attached by addition, subtraction, multiplication, division. I think we could put in that -1 to see that we're attached by multiplication, and so we can undo that by division. And we end up with x is less than or equal to -3. Notice that we did have to switch the inequality sign, and we switched because we divided by a negative. Then, since we're still doing this, let's go ahead and graph that too. Well, no, let's hold off on the graph because I'm not quite sure where -3 is going to fit on the number line. Over to the blue equation. 3 steps to solving an equation, usually distributive property first. So negative 3 is less than 3x minus 6. Now just isolating x because there are no like terms on either side. Very nice. So to isolate x, maybe we should add 6 to both sides. SAD map, right? Addition and subtraction first. That gives me 3 is less than 3x. And last but not least, we should probably go ahead and divide by 3 to give us 1 is less than x. Now, 1 is less than x is me reading this forwards. If you read it backwards, it says x is greater than 1. And so it might actually make more sense for us to switch the sides for the x and the 1. But if you do that, again, remember the teeth on the inequality, right? It's currently trying to eat the x over here. So if you switch the two sides, the inequality better still be trying to eat that x. And so we come to our final conclusion of x is either numbers that is less than or equal to 3, or x can be numbers that are greater than 1. How do we graph this? Well, we do something like this. Negative 3, negative 2, something like this. Let's make sure we get both of those key values on there, negative 3 and positive 1. And then we go to each of the numbers. So negative 3, open circle, 1, open circle, and then we think, are either of them filled in? Well, we can't be equal to 1, so that stays open. However, I think we can be equal to negative 3, so we go through and fill in negative 3. X can be values less than or equal to negative 3, less than, more negative, looks like this. Or x could be numbers that are greater than 1. Numbers greater than 1 look like this. All right. Now, this is really as hard as today gets. You have 2 things to accomplish for the rest of today. The first thing is a few more practice problems, right? 1, 2, 3, 4, 5, 6 practice problems. And then you have some contextual problems, problems with context, word problems, if you will. So I would suggest probably trying to solve these 6 problems first, and then unpausing the video, and I'll work through them a little bit faster though. And then, once you're confident with those, move to our 3 contextual problems, and you might need a calculator or something with those, and then work through those as well. Okay, so good luck. Go ahead and pause me, and then see what you can do. And you're back. Hopefully things went pretty well. I'm going to treat this one, I'm going to go pretty quickly through these since you already had time to look at them. So let's see what I can do. We need to subtract 3 from both sides here. This is an OR, so the equations are completely separate from each other. Don't treat them the same, and this is x is less than negative 2. My other one, we need to subtract 3 from both sides. 2x is greater than 4. And then, of course, divide by 2. No reason to flip the inequality sign anywhere on here because there is no negative being multiplied or divided. So it looks like my final answer is that we can graph x's that are less than negative 2, or those x's are perfectly allowed to be greater than positive 2. Here's my number line, right? Negative 2. Nothing too bad, except I almost forgot how to count, so that was awkward. And then we look at this. X can be less than negative 2 or greater than positive 2. I don't see any equal signs, so we can leave our circles open. And I think we have finished this off just fine, right? Great. Here's our next. Negative 1 is less than or equal to 1/2 x, which in turn has to be less than 2. I left some gaps here because I saw there's a 1/2 that's multiplying by x. You have 2 options here. One option, and I'm going to erase this, is you can divide by 1/2. But that scares some people when they're like, ooh, we're dividing a fraction within a fraction, kind of looks gross. So I would say maybe instead we can just multiply by the reciprocal. We've done that before. I'm going to multiply by 2 over 1, and I think that's going to cross-reduce everything here. Just leave us with x. However, to keep all things balanced, we need to multiply the other sides by 2 over 1. But I'm not going to multiply by 2 over 1 because 2 over 1 is just a fancy way to say 2, and why use a fraction if you don't have to? I think that's going to give us negative 2 is less than or equal to x, which is less than 4. And then going through and solving this, right? Negative 2, negative 1. There we go. Did that again. -4. Okay. And we go through. We want to do maybe an open circle on -2 and an open circle on 4. Do either of these have equal signs? Not that one. Oh, this one does, though. There's an equal, so we need to fill that in. And it tells us that x has to be a value between -2 and 4. Well, to show the values between -2 and 4, we shade in. This is an and compound inequality. Third one. X is almost isolated. There's that invisible -1 here, but it's not isolated because -1 is multiplying, so we should probably divide all three parts by -1. We do 4 divided by -1, that's -4. These undo each other, leaves us with a +1, and 2 divided by -1 is -2. Did I do everything right? Ooh, I'm not sure I did, because doesn't it look like we multiplied by a negative? Don't I have to flip these inequality signs? And it look like this and like this? Right? Now, we need to think about this problem. This problem is really, really strange. And honestly, I'm pretty sure I wrote this. This problem could be a bad one, but let's still look through it. Because if I split this into 2 pieces, so I'm going to split one piece here and one piece here. This is telling us that x, I'll do it in green first, x has to be a number that's greater than -2. Okay, and we can see -2 and -4 have to be on my number line, so let's do that. -4, -3, -2. Then we'll get the rest of those on there. Now, I think what's going to end up happening is we probably get no solution here, but let's double check. So x has to be a number greater than -2. So here's -2, and greater than that is over here. But because this is put together, this is a compound inequality that uses and. And so the other part of this, and this is going to be a little tricky, notice the teeth are facing the 4. So when I rewrite this with the x on the left, I'm going to keep the inequality looking like this. It says x has to be a value that's less than -4. And it's an and. So what number can you think of that is less than -4, but also at the same time greater than -2? Well, I can't think of anything, right? This isn't an or. If it was an or, that shading that I had up here, the shading that's up there right now, is the right answer. However, it's not an or, it's an and. And I don't think there is a way that we can do that. I think this is an example of something that has no solution. It's okay if you're like, wait, I just thought it was always between -4 and -2. We probably won't give you something this crazy challenging, but it is good for you to know that there are no solution problems. Let's look at a couple more. Problem 4. We'll need a little space here, and we're going to separate this because this is 2 just completely separate problems. We have 2/3 x is less than a little room for the 4, and then we also have, instead of x over 5, maybe we should get in the habit of saying x divided by 5 is greater than or equal to 2. Well, let's start maybe with this left one over here. How do we start to undo things? Well, the only thing that's attached to x is 2/3, and we know we use the reciprocal. And I decided to do the reciprocal wrong. There we go. The reciprocal, so 3/2. And you'll notice that on the left side, everything here cross reduces and just leaves us with x. Very nice. But on the right side, we'll probably want to make 4 a fraction. And then you could say that this is 12 divided by 2, which is 6. That's fine. Or you could cross reduce, and you could say 4 divided by 2 is 2, and 3 times 2 gets you 6. So x has to be a number that's less than 6. Or, well, if you think of this as x divided by 5, we can undo dividing by 5 just by multiplying by 5. Right? These ones undo each other, cross reduce, and 2 times 5 is 10. And I think that's not too bad. There is an or in the middle here, so x is either values that are less than 6 or greater than 10. So 6, 7, 8, 9, 10. Nothing too awful, I think. Well, we need an open circle around 6 and an open circle around 10. X can be greater than or equal to 10. Oh, equal, closed circle. And then shade to the right. Okay. Or x can be strictly less than 6, can't be equal to 6, so we don't fill things in. Looks something like that, and we have our answers. 2 to go. 0 is less than or equal to something crazy in the middle, which is less than 10. It looks like there's parentheses, so I think we should probably go through our 3 steps of solving equations. Step 1 is we need to distribute. 0 is less than or equal to, I'm going to put the 1 in front of this x, 1x plus 3x minus 6. And then the second step, of course, is to combine like terms. No like terms on the side with 0, no like terms on the side with 10, but in the middle I think I see 1x and 3x, which is certainly going to combine to make 4x. And then we just have to find the side with x. That happens to be our middle side. I'm not really sure I can say middle and side in the same sentence and have it make sense, but you know what I mean. And then we need to isolate x. Well, to isolate x, I think we can just add 6 to all 3 sides. This is SADMAP now. We undo addition and subtraction first. We have 6 is less than or equal to 4x, which in turn is strictly less than 16. And last but not least, we should probably divide everything by 4. When we divide everything by 4, oh, sorry, big yawn. You'll notice a couple things. First, 16 divided by 4 comes out nicely with 4, but 6 divided by 4 doesn't. In fact, if you do 6 divided by 4 on your calculator, you'll get a decimal, so I'll show you both answers. You could reduce this by 2, right? We know how to reduce fractions. That's 3 over 2. Or you could say that 3 divided by 2 or 6 divided by 4 is 1.5. Right, so 1.5 is equal to 3 halves, whichever one you use, and regardless, that has to be less than or equal to x, which is less than or equal to 4. I'm probably not going to put the exact decimal on here, but we can at least use 1. Actually, there might even be enough room. I bet we could start at 1 and we'd have enough room. 1, 1.52, 2.53, 3.5. Oh, there's plenty of room. Look at that. I could have done even better. But oh well. We are not perfect all the time, are we? Negative. 1.5 is one starting point, and 4 is the ending point, I think. Can we be equal? Well, yeah, x can be equal to this one, so closed circle. We can't be equal to this one, so open circle. X is greater than 3 halves, so that's this way. But x also has to be less than 4 at the same time. And so I think we can fill these two in and say we have our graphed solution. Last one. 2 is less than x, which is greater than 3. 2 minus x is greater than 3. Or let's make 2 separate problems, try to color code this too. So we have 2 minus x is greater than 3. Or x is greater than or equal to negative 1. Oh, look, this one's already solved. I don't need to do anything. That is awesome. Couple things to think about for the problem in blue. You have a few options here. I'm going to give you one you probably wouldn't think to do because it's always nice to do things differently. I might notice that x is really almost isolated, but it's a negative x instead of a positive. So one thing I like to do is I actually like to add 1x. Because that's going to make all the x's positive. Now, you don't have to. You could have subtracted 2 first from both sides, divided by negative 1, but it's always good to look at a different method to do a problem. This becomes 3 plus 1x. Well, why did we do that? Well, we're trying to isolate x, so what's still attached to x? We clearly have a 3 that's adding, right? We always use the sign in front of the number, so we're adding 3, and then we're multiplying by positive 1. So let's undo that adding 3 really quickly. And we end up getting negative 1 is less than, and this is 1x, but if there's a positive 1, don't we not need to write that? I think we can just put x. And then we're done. So we actually get away with only having to add and subtract on this problem. If you had solved this traditionally, you would have divided by negative 1 at some point, but this is just showing you a nice other way to do it. And then don't forget that we could rewrite this with the x on the left, negative 1 on the right. Teeth are facing the negative 1. And then, of course, we have our or, and then the other one is x is greater than or equal to negative 1. Let's get these graphed. X is less than negative 1. Well, we definitely need negative 1 on our number line, I think. Good practice with your positives and negatives here, too. That's why it's always nice to write in those numbers. Once you can cement in your mind which way negatives go, which way positives go, it's going to make you that much better of a mathematician. The blue equation says x has to be less than negative 1, so open circle there. And then the green equation says x has to be greater than or equal to negative 1. So negative 1 again, but equal to means we can fill this in. Sticking with the green equation, greater than or more positive than -1 is going to move us to the right, something like that. However, x less than -1 means we also go to the left. And look at this. Notice that the number line is filled or shaded everywhere, including that middle circle. So this would actually be an example of all real numbers. Alrighty. Well, that brings us, I think, to our word problems here. So why don't you guys go ahead, pause me. You will probably want a calculator at some point for some of this. Some of the word problems can be a little bit tricky. You don't have to have a calculator, but I think it will help you out. I will show you how to do it without a calculator in case you're curious. But yeah, let's see what you guys can do here, and then unpause me once you're ready. Welcome back. I think our first problem hopefully is not too terrible. This is actually an election year. It is the dreaded 2020, and we have a poll that's showing a candidate is projected to receive 57% of the votes. However, most polls have a margin for error. Then this one is plus minus 3%. Sometimes you'll see them write it like this. Well, what that means is you take the number that's projected, 57%, and say we think they're going to receive 57% of the votes, but we could be off by an amount. They could receive at most 3% more than that, and at least they could receive 3% less than that. We're 100% confident that'll happen. Well, how do we show that? Let's go ahead and define how many votes the candidate actually receives in terms of a percent. So the votes we don't actually know. We're just going to call that x. We're going to say x is going to be the number, or really I should say the percent of votes that they actually receive. Well, we know that x is going to be in between two values. We'll talk about the equal to in just a second. We know that the biggest or the largest percent of votes that they could ever receive is 57% plus 3%. And the smallest that they could receive is 57% minus 3%. That's what our plus minus here equals, or means. So when we clean this up, 57 minus 3 will be 54%, which is less than x. And 57 plus 3 is 60%. Now, I bet logically you could have seen this. You're like, plus minus 3, well, that's 3 higher than 57, 3 lower, x is between that. Yes, you're right. What about the equal to? Well, because you can receive exactly this, and they said 3% higher, I think we can put equal to's under both of them. You can have equal to 60% or smaller, and equal to 54% and larger. And that's it. Easy peasy. Let's take a look at our second one. Greyhounds, the dog, not the bus, have a super high metabolism. It means they process their food and create energy really quickly. And because they're processing that food quickly, they have to eat a large amount of food every day. Mr. Grant, one of the math teachers at our school, has a greyhound named Jake. Jake weighs 78 pounds. And in order to stay healthy, Jake has to eat between 4 and 8% of his body weight daily. Please go ahead and write a compound inequality to describe the amount of food in pounds Jake must eat each day to stay healthy. Well, we, I think, need to show that the amount of food is in between 4 and 8% of Jake's body weight. So let's talk about how much food Jake must eat first. So the food that Jake must eat, maybe let's call it F for food that he must eat. And we know that the food he has to eat has to be in between two things. It has to be in between 4% of his body weight and 8% of his body weight. Well, what is his body weight? I think they tell us over here that his body weight is 78 pounds. So I think what you'll have to do then is actually take 4% of 78 and 8% of 78. Some calculators have percentage buttons. You can make that work. Other calculators, and I'm going to use a little bit of room here, other calculators might actually make you rewrite the percentage as a decimal, and we've done this before. You move the decimal 2 spots over, so it's going to become 0.04 times 78, that'll give us 4% of 78, is less than the amount of food he has to eat, which is less than 8%, so 0.08 times 78. So you're going to want to whip out that calculator and see what you get. I'm going to do long multiplication over on the side while you're working with your calculator. It's always good practice, right? Just to remind you of how everything works. We do 4 times 8, that's 32. And we'll write a 2 and then carry the 3. 4 times 7 is 28, plus 3 more gives us 31. Placeholder 0, 0, 0, easy enough, add it together, 3, 1, 2. Well, then you'll notice that we had 2 numbers to the right of the decimal place, so we need to have 2 numbers to the right of the decimal place, and it looks like we get 3.12 pounds. Let's try our other one. We also had to do 78 times 0.04, 32, 28, oh wait, I already did this one, 0.08. Oh man, okay, second try. Day's getting long, I guess. 8 times 8 is 64, carry the 6, that's 50, 8 times 7 is 56, plus an extra 6 is 62, and then a placeholder 0 gives us, I should have put the plus over here, gives us 624, 2 numbers past the 0, so we get 6.24 pounds. Therefore, if we wanted to write our final answer, and I know I ran out of room, you might have to write small here. I think Jake has to eat between 3.12 pounds and 6.24 pounds, and he can be equal to that. And he can have exactly 4% to 8% of his body weight. That's a lot of food. Okay, and let's move on to our last problem. This one deals with the planet Mars. Mars has a maximum temperature of 27 degrees Celsius at the equator, right in the middle of the planet, and a minimum temperature of negative 133 degrees Celsius at the south, or sometimes called the winter pole. Mars has a cold pole and a warm pole, or I guess warmer. Now, I gave you these temperatures in Celsius, and these are real temperatures for Mars, but you might not be too familiar with temperatures in Celsius. You might not know, wait, is 27 degrees warm? Is negative 133 cold? Or, I mean, like, it seems like both of these are really cold, right? The United States is one of, I think, maybe 2 or 3 countries remaining that doesn't use Celsius. So you should probably be somewhat familiar with converting between Celsius and Fahrenheit, or at least know a few temperatures if they're warm or not. Now, if you don't, that's okay, because I'm going to give you an equation that's going to help you convert between Celsius and Fahrenheit. And it tells you that the Celsius degrees are equal to 5/9 of the Fahrenheit degrees minus 32. But I think that's actually not super helpful. I mean, imagine we wanted to convert 27 degrees to Fahrenheit. Well, this is clearly a Celsius temperature. So if I used this equation down here, we'd do 27 in for Celsius equals 5/9 times Fahrenheit minus 32. And then if we wanted to actually find the Fahrenheit temperature, we'd have to go through and solve this equation, maybe distribute the 5/9 and multiply by reciprocals and do all that. So that's what we're really looking for when we have an equation to convert between temperatures, is we want to make sure that the independent variable, the input, is the variable that we're interested in. Right now it's not. So that is the issue with why this equation is not very helpful. But the nice part is we have these algebraic skills that will let us turn this equation into something more helpful. So let's rewrite the equation over here. You might have to write kind of small. I'm going to zoom in. Celsius equals 5/9 times Fahrenheit minus 32. And what we're going to do is we're going to rewrite this equation so that Celsius is the input and Fahrenheit is the output. We're going to switch the independent and dependent variables. And the way we're going to do that is we are going to isolate F in this equation. I'm giving myself a little bit more space because I realize that there's 2 ways that we can do this. Option 1 is you could distribute 5/9. But I don't really want to do 5/9 of 32. That seems like a gross number. I think so. Instead, what I'm going to do is just start by removing this 5/9 by using the reciprocal. And the nice part is if you multiply this whole side by the reciprocal, it's just going to immediately cancel out with the 5/9 in front. And so we need to multiply by 9/5, the reciprocal of 5/9 on the other side. We'll notice that these ones cancel. And that gives me Fahrenheit minus 32 on the right side. We don't need parentheses anymore. There's nothing acting on the parentheses outside now that we've undone the 5/9. The other side, though, is just going to be 9/5 C. And don't forget, literal equations, the ones that have more letters than you're used to, are way easier because you don't actually have to do any math. We're just writing 9/5 next to it. And now I think there's only one more step to isolate our Fahrenheit. Fahrenheit is being subtracted by 32, so we should probably add 32 to both sides. Again, these literal equations, super easy. We just write everything next to each other. 9/5 C plus 32 is equal to a Fahrenheit temperature. And we've done it. We've worked our equation using algebraic rules to make sure that our F, our Fahrenheit degrees, is the output, and C is the independent variable, the input. Well, how does that help? Well, we're going to go ahead and use this literal equation to convert the maximum, that's 27 degrees, and minimum negative 133 degrees Celsius temperatures for Mars into degrees Fahrenheit. So we can actually see, is Mars cold? Is Mars hot? And you can make a prediction too, but let's go ahead and work through. You might want a calculator here too. I'm going to just do some quick mental math. I'm not sure it'll come out very well though. So we're going to divide this, and we're going to start with my Celsius equals 27 degrees. That was my warm one, and I'm going to use this equation over here. So it's going to say our Fahrenheit temperature is equal to 9/5 of the Celsius degrees, right, plus 32. And then we have a little bit of math to do here. I think this one is going to be pretty gnarly. I would heavily recommend that you guys pull out a calculator here. But what I'm going to do is maybe set up the other one and then do the calculations all at once. So when I do the other temperature, the cold temperature, was, I think, negative 133. Let's double check to make sure I'm not lying to you. Negative 133 degrees. Very nice. And then Fahrenheit equals what? So hopefully you have your calculator out by now. I'm just going to pull up the Desmos Scientific Calculator. It's a free app on your phone, and I actually like it better than most of the calculator apps that come standard with phones, because Desmos will let you do multiple operations at once. So I'm just going to search for Desmos Scientific Calculator. Pull it up, and we get something like this. So, looking at this very quickly, our first one is going to be 9/5, and we can just use the division symbol to get that divided by 5, right? Times 27 plus 32. And it says we get 80.6. So 80.6, we should keep our colors consistent. Okay. And then we have to do the other one, 9/5 times negative 133. So 9/5, and I'm just, this is again the nice part, I'm just going back to what I've already typed in, hitting delete a couple times, and then I can put in the new one, negative 207.4. Up, colors again, here we go, negative 207.4 degrees, and I should probably put Fahrenheit on both of those so we don't get confused. Alright, well, thinking about those temperatures, is that warm or is that cold? And what I think you'll notice is it's a little bit cooler than Earth, right? Earth, we just had one of the hottest temperatures ever. I think it was in Death Valley, and it hit around 130 or so degrees Fahrenheit. That's about 50 degrees cooler. Then you have really, really cold temperatures down in like Antarctica or maybe up in Alaska, something like that, that definitely drop into the negative hundreds, but I don't think they go quite that cold. So what it seems like is they've just shifted the temperatures on Earth a little bit colder than normal. And I think that actually might make sense for part D, because if you think about where Mars is in relation to the solar system, right? Mercury, Venus, Earth, Mars. Mars is further away from the sun than we are, and so it should probably make sense that it's a little bit colder because it's further away. Let's go ahead and take a look at part E. Part E says write a compound inequality to describe the temperatures on Mars. Well, that's easy. We'll take the smallest one, negative 207.4 degrees, and we'll take the largest one, 80.6 degrees, and then maybe let's just let FU stand for the temperature Fahrenheit here, and we're going to say our temperature Fahrenheit has to be less than or equal to the smallest and less than or equal to the largest. Fahrenheit reading from right to left has to be greater than that small temperature, but our temperature also has to be less than the largest temperature. Graphing this, I'm going to be incredibly lazy on this. I'm sure you won't judge me too much. We're going to say that, we'll use the bookends here. We'll say that this is negative 207.4 degrees, and this over here is going to be 80.6 degrees. We can use a closed circle. We're allowed to be equal to those temperatures, and then we're just going to shade in everything in between. Right? Nothing too terrible. This is showing us all the possible temperatures on Mars are in between those two values. Now that you've gotten through this, you are really done with your physical and digital day lessons. Again, make sure you listen to your teacher on how to turn this in so you can get credit for it. And then be ready because next class we're going to start reviewing for our first test.